So here to talk about purpose-built machines for the die-cast industry and for die-cast parts. So we'll kind of walk through, why purpose-built, why would we be interested in that, and talk about something we call ROI design, and then finally talk a little bit about some of the industry trends that we see going on today. And die-cast is a very, ubiquitous component. You can't walk through a doorway without walking past a die-cast component. They are everywhere. They're in the consumer appliances, electronics. You go do a knuckle drag down through your local Home Depot, there's die-cast parts all over the place. And then the biggest one really is automotive. 44% of all die-cast components go into automotive components, and an average car has somewhere between somewhere around 100 casting components in it. That's one of the trends that we'll talk about at the end, and that number is falling dramatically. And it's not necessarily a bad thing. Don't get spooked by that. It's just a change in the way that they're designing some of these parts. But really, 90% of all finished goods that are out there contain a die-cast component of some sort. So huge industry, very important industry, important to everything that we do from a manufacturing standpoint, important to Makino. And over the years, we've gotten to know a lot of customers like yourselves that are in the die-cast industry, and we listen to the feedback and listen to the stories and the challenges that you're seeing on a day-to-day basis. Pricing pressures are huge. You're facing mandatory per-piece cost reduction from your customers. Production or durations of your orders, the length of those orders is getting compressed quite a bit. Being challenged to provide value-added services, not just here's the die-cast part. Your customers more and more want the completed part that they can run right into their assembly lines. And then increasingly, we're seeing things, a lot of pressure from an environmental and energy standpoint, and regulations being ramped up that the die-cast industries are facing. In thinking through this and listening to our customers, and they get that application where they need some machines, and talking with them, and what do you want to accomplish with that next purchase? And we hear things like, the unplanned downtime is killing us. Okay, so as a builder, we need to help eliminate that unplanned downtime. We're out of room, we need a compact machine. So we need to think about efficient use of floor space when we design the products. Constantly fighting to hold tolerance. So I need something that's going to help you eliminate scrap parts. Can't find the operators. We need to help you with automation. This is a die-cast facility. We don't have chip cutting expertise. Okay? How can we help with turnkey solutions? And then finally, our productivity per spindle has got to go up. Okay? So we need to help with reduction of cycle time. So in my talk today, I'm going to focus kind of on two areas, but the key is, how can we reduce our per-piece cost of the components that we're making today? And I'm going to talk with you about two key areas. One is eliminating unplanned downtime, and the other is what you can do to reduce cycle time and how important that is. So let's start out with an example, just a theoretical example. We're going to talk about an automotive component, transmission valve body. So situation is, there's two operations that it takes to make this part complete. There are 4 parts per fixture, and 13 tools go across that part to make that part complete. So we've won an order for 750,000 parts per year. So this is going to go across a couple of engine platforms. And it's a 5-year program. The negotiated per piece price is $16 a component. The capital equipment that we're going to use is going to be financed. We're going to finance it over a 60-month term. And all the machines in this case, just for simplicity, are going to be manually loaded. So the machine that we're going to need to use for this particular application is going to be a 400-millimeter horizontal machining center. That's really the workhorse of a lot of these kind of components. You'll find them on a 400 or 500-millimeter horizontal. Those are some of the things that, just spec-wise, what you might want on the machine. You may want a coolant temperature controller, 1,000 PSI, auto doors, fixture hydraulics. At the end of the day, this particular machine, the net negotiated price based on this particular order was $370,000 per machine. So we're going to take some of that data and we're going to plug it into a spreadsheet to help us understand what are our real costs. And in that spreadsheet, not only are we going to take into account the machining center, but we're going to take into account the horizontal machines, some of the ancillary equipment. Maybe you got parts washers in there. Maybe you got material handling in there. We're going to look at the durable tooling, your fixtures. What are the costs of those? We're going to add in your operating costs, labor, perishable tool costs, utilities, floor space cost, and maintenance, and factor all of that in to just kind of get an idea and help us compare some different scenarios of running these parts. So we're going to look at a couple of different machines. Machine A. With Machine A, the cycle time on making this part is 157 seconds. And based on that, remember, we got to make 750,000 of these a year, okay? Based on that, you need to have 7 machines to do that. When I plug all that into that spreadsheet and factor in all of our other costs, that tells us that basically you've got a total cost on that work piece of $14.23 each, okay? Let's look at another machine. So we find another brand machine. That particular machine, when you run it through the cycle time process, it runs at 137 seconds, or 136 seconds. Not seemingly like a big deal, right? But at the end of the day, given that kind of volume, you just got rid of one machining center. And you're not getting rid of just one machining center. All of a sudden, you eliminated a pair of fixtures, a tool set, floor space. If you're doing automation, you got rid of automation costs. There's labor costs. So there's a significant savings to shedding that one machine from that application. Machine C. Machine C actually does it in 115 seconds. So now we're down to 5 machining centers to do this job. And now we're going to make this part for 55 cents less than option A. Doesn't seem like much, but when you wrap it into the spreadsheet and run through all the numbers, all of a sudden you go from a baseline over the life of the product to machine 2, you got $1 million more profit. Machine 3, you got $2 million more profit. There is no single factor that is going to save you more money in making your die-cast components than the overall cycle time, okay? So let's talk about it. You're just 100 steps outside of this room. You've got a sea of machine tools. There's all kinds of different solutions that will make that part, and then will make that part well. But there's certain characteristics on a machine tool that are going to help you make that part better and faster and make you more money, put more profit into your company. So that's what we're here to talk about today. What are those factors? What should I look for in a machine tool that's going to help give me that advantage and make me more profitable at making my parts? We do a lot of turnkey work at Makino. Okay? We see a lot of these parts. And we've collected a lot of data over time and looked at what does it take to make a die-cast part. And when we kind of laid it all out and did like a Pareto document or diagram, what we found is these are kind of the key things that happen during the cycle time. Okay? This is how that total cycle time is spent. You know, a lot of it is spent in tapping, there's face milling, drilling, in milling, but then there's also a lot of time that's unproductive non-cut time, and especially rapid traverse time. 34% on average of these, we looked at about 100 parts, 34% of the time on these parts was spent just going feature to feature, moving feature to feature. And you can kind of see it, you know, as an example, you look at that part there, it's got a lot of holes that get drilled on it, okay? So that machine is going to spend time moving around to positioning to each one of those holes, and those holes are about 2 inches apart, okay? So if our goal is to get rid of that rapid traverse time as much as possible, it's not making any money, how can we trim that out of there? So how do we do that? Well, the knee-jerk reaction is, let's crank up the speed limit, okay? If speed limit's 60 miles an hour and I got to move from each one of these features, if I could go faster than 60 miles an hour, I could cut some time out of there, right? Kind of logical, it makes a lot of sense. And again, when you walk across the sky bridge there, you're going to see machines over there that are breaking that speed limit. They are using a different technology. They're not using ball screws. They're using linear motors, and they have got some blistering fast rapid rates. There's some machines over there that are upwards of 90 to 120 meters per minute as far as the rapid traverse rate. So you may think, cool, that's going to really help me be more competitive and more productive at making my machines or my parts, right? Not quite the case. And we know this from past experience. Back in the late 90s, early 2000s, we had an industry-leading machine called the A55. It had rapid rates of 84 meters per minute. And it was replaced by a machine called an A51 that had 50 meters a minute. And everybody pulled us aside and said, what are you doing? This is crazy. You were at 84, you were leading the industry, now you're at 50, you're with a lot of more competition. Why would you do that? And today we're relying on a machine called the A40 to do these kind of parts that's purpose-built for die cast. And it's at 60 meters a minute. Well, the reason is that if you look at that acceleration curve, the time that it takes to get from feature to feature, okay? When you start out, you're at that steep portion of the curve. That's called the jerk portion of the curve. That's where the rate of change in acceleration is constantly ramping up. Well, with a slower machine, the seemingly slower machine, we get to that full rapid point faster than the other one. The other one is still accelerating. The theoretically quicker machine is still in the acceleration process, and we're actually able to get to our destination faster with a machine that on paper is a slower machine. Okay? Here's what it looks like. This is a chart of a machine at 90 meters a minute rapid rate and a machine at 60 meters a minute rapid rate. Along the bottom scale there, you've got the distance between features. Okay? So does that 90 meters per minute save you some time? Yeah, it does. But if you look at the chart, it's not until you got about 12 inches between feature to feature that machine is going to beat the slower machine. And when you think about your die-cast parts, how often are you going 12 inches from feature to feature before you need to stop and drill a hole or stop and tap a hole? So for a typical die-cast part, in this case, the machine with the slower rapid rate is going to turn out parts for you faster. If what we want to do is focus on the acceleration of getting from feature to feature, then we need to look at it a little bit differently. And we're gonna pull out some physics here. We're gonna look at Newton's first law of motion. And that says that an object at rest stays at rest. An object in motion stays in motion. That's inertia. So we're gonna focus a little bit on inertia here. That object stays at rest unless something acts on it. And here's the formula for Newton's second law. Force equals mass times acceleration. We've all heard that one before, right? If I want to improve, we're going to flip that equation around a little bit. What we want to focus on is the acceleration, okay? So acceleration is force divided by mass. So if I want to improve my acceleration, there's two ways I can do it. First way is to increase the force, okay? We all love doing that, right? Put a bigger engine in it. That is going to make everything better. Get a bigger hammer. That makes it better, right? Well, in the world of making these parts, putting a bigger motor in the machine is going to make the machine more expensive. It's going to make the machine bigger. It will get you better acceleration, but it's not really practical for what we're trying to do. Okay? So if that doesn't work, we need to go with option 2. And option 2 is, what can we do to shrink the mass and give us better acceleration that way? Okay? And we call that intelligent reduction of inertia. So intelligent ROI solution. So we're using this design philosophy to make machines that are purpose-built for near-net shape. And die-cast is very much near-net shape. So the conventional versus the ROI solution. So in order to understand that, let's kind of look at the kinematics of a horizontal machining center. So here's our bed casting. So everything builds up on the bed casting. There's the column, there's the spindle, and there's the table. So the motion that we're looking to optimize, the x-axis, we're moving that column back and forth. Y-axis, we're going to move that spindle and the spindle carrier up and down. And then z-axis is going to be the table moving in and out. So what can we do to look at those three moving elements, those three moving systems, and optimize those systems with the ROI design concept? Get the mass out of those components to allow us better acceleration. Let's start with the x-axis. So the x-axis is that column moving back and forth. And we like a tiered column design because it takes all the forces and it redirects them back into the bed of the machine, which is where a lot of your rigidity is coming from, and it allows you to get full utilization of the y-axis. But by doing that tiered column, we take a big chunk out of that column, and instead of moving a big trapezoid back and forth, by taking that triangular section out of it, we're removing mass from that column. That's going to help, but we can do even better. We can go even further. And what we did is we looked at the column design. The one on the left is from an A51, okay? That uses a very common design column. It's a double column that is linked at the top and at the bottom. Very rigid, very strong, ideal if you're looking to do 40 horsepower cuts all day long. We're not going to do that in a die-cast part, okay? So what can we do to provide the geometry that we need, but with less mass? The one on the right, on your right, is the column for an A40. That is designed based on a skin. So instead of these huge, large elements that come up the side that's linked to top and bottom, that's more of like a box, like a cardboard box with the strength and the rigidity is coming from the skin of that material, okay? By doing that, we have the strength and rigidity that we need for the part application, but we've cut the mass by half. Huge reduction in weight there. And it's going to improve our x-axis responsiveness. Here's an example. We look at the distance that it takes to get to that full rapid, and then how much time does it take to get to full rapid. So we're comparing a typical machining center, in this case it's a Makino A51, to the A40, and you look at how short of a distance it takes to get to that full rapid in X, and how much less time that it takes to get to that destination. So that may seem like a lot, but small changes that you do day in, day out, thousands and thousands of times a day, stack up and make a difference. Okay, so that's the x-axis. How about the y-axis? So it's responsible, the spindle carrier and the spindle is responsible for all y-axis motion. So we're going to use the same ROI principles, and we're going to reduce the mass out of the spindle carrier and the spindle itself. And there's the two views. You can kind of see the reduction of mass just from the smaller elements that are there, okay? Half the weight. And since inertia depends solely on the mass, we get the same sort of results that we saw on the x-axis. So now we were more responsive on the x by changing the column design. We're more responsive on y by changing the spindle and the spindle carrier design. And if you stack it up, if you look at x and y axis from a number of different machines, we're 14% faster than a typical machining center by focusing on this ROI design. All right, what about the z-axis? Z-axis is a little bit more complex because we've also got the b-axis rotary table on there as well. It's responsible for all z-axis motion and the b-axis, which is a direct drive motor. A couple things we're going to do here. Number one is we're going to change this machine tool from operating on 200 volt, like most of them do, and we're going to operate on 400 volt. What that allows us to do is have a smaller, more compact, lighter motor that produces the same torque and horsepower that the 200 volt does. So we've reduced mass by just changing the voltage that the machine operates under. 29% reduction in the Z and the B axis mass. So that's going to help us as well. And we get the same sort of results. In fact, we're getting 20% improvement because that 400 volt responsiveness also helps us from the Z axis motor standpoint to be quicker. So conventional versus ROI design. All right, so that's kind of how we've attacked the rapid traverse and got that rapid traverse time down. Take that unproductive time of moving from feature to feature that's robbing you of profitability and give that back by focusing on an ROI type of design. But that's just part of the story. We've also got cut time. So what could we do to eliminate some of the cut time? What are the systems on that machine that have an influence at that? And the number one is the spindle, okay? So we went and looked at the spindle more from a perspective of what, if we're focusing on near net shaped parts, what does that spindle need to look like? 12,000 RPM, 20,000 is an option. Really hits the sweet spot of what you need for these kind of parts. Cat 40, HSK 63, pretty much an industry standard. Jacket cooling. Then you get down to the power. 11 kilowatts of continuous power. Not quite what you'd be used to seeing. But, and these kind of parts, you're never going to have a situation where you've got a chunk of cast iron in there that you're looking to slab a ½ inch of material off of. Having a spindle that can do that is a detriment to cutting your die-cast parts, and I'll show you why here in a minute. So typically on a high-pressure die-cast component, we're looking at stocks of no more than 1/8 of an inch. Okay? So we don't need a high-power spindle. So we're going to get back to the physics again, and this one gets a little bit more technical, but I've got some props here to help explain it. It's all about the inertia again, but this one's a rotational inertia. That's the formula for rotational inertia, and that one takes a little bit more to wrap our head around. But basically, it goes back to the mass. If you look at the equation, mass is right up there. It's a function of the numerator, and then the radius of that rotating mass also comes into play. So by removing mass and make that rotational radius smaller, I am going to be able to reduce the rotational inertia, which is what our goal is. Okay? So there's a look at, if you take the spindle, the rotating portion of the spindle, what you see in pink at the top and blue at the bottom, that's the rotor. That's the rotor portion of the motor. And then at the end there, you can see your spindle taper interface where your tools are going to go. So that's a look at a typical 40 taper spindle versus one that's designed for near net shape. So the A40. There's a cross-sectional view of it. And so we've reduced the rotational inertia by 65%. I brought some props with me to kind of show this. And Darren, can you help me out here? Okay, so we got a couple of yo-yos here. Not us. Couple of yo-yos here. All right. Are you ready?
I'm ready.
All right. 3, 2, 1. See the difference? That's rotational rotational inertia in action. So this is the spindle designed for near net shape. Less mass, smaller radius that's rotating, and that's going to give us better performance. Thank you, Darren. Yep. There's a look at the actual spindles. There's an A51 versus an A40. And these are both Makino solutions. And so here's, if you run the test and run from 1,000 RPM up to 14,000 or 12,000, what you're seeing there is the time that it takes to do that acceleration. There's a number of different horizontal machining centers. One of them is a Makino, 2 of them are our competitors. But that gives you an idea of what it takes to ramp up to that full programmed RPM in seconds. Okay? And think about every tool that goes in that spindle sees a ramp up and a ramp down at least once, right? But what about tapping? Every tapped hole, you're advancing and retracting that spindle. So that same acceleration, deceleration advantage is going to come into play hundreds, thousands of times per day as you make your parts. And so the one in red, that is based on an M6x1 going 3 pitches deep or 3 diameters deep, and that's the cycle time that it would take based on different RPMs of tapping. So a couple of interesting things about that is you see every once in a while you walk around looking at a spec or walking around the show floor, you'll see somebody that says, hey, we can rigid tap at 9,000 RPM. Well, that's great if you've got a tap hole that's this long, but that doesn't exist. That's not in the design of parts. That's designed to be misleading on the specifications. Really, if you look at it, it kind of saturates out at about 2,000 RPM. Beyond 2,000 RPM, you're not gaining any time by having a faster tap speed, okay? It's really all about the rotational inertia of the spindle. Here's an example of an A40 doing some tapping. So that's that advantage of that rotational inertia in action there. That was 8 M5, I think those were tapped holes. So again, reduction of inertia solution. All right, let's talk about some other technologies that are going to help you in reducing cycle time on these parts. First one I want to talk about is inertia active control, and then we'll get into some of the advanced motion control techniques. Inertia active control is we're looking at the elements of the machine that are moving and what can we do to optimize those. We have a system on pretty much most of our horizontals, most of our production horizontals, where when you put your fixture on that pallet, you have a single touch button that you can select, and it will rotate that pallet back and forth, and it will sense how much work that motor's doing. And based on that, it will adjust the acceleration and deceleration curves. We have to design the machines for the maximum payload that's in the spec. So that's how they come out of the box, is designed for that. But the reality is what you're putting on top of that pallet is probably not at that maximum. So this gives you the ability with a single touch button to set up and optimize pallet 1 and pallet 2 for your particular application and take that pallet index time and optimize it. So same thing works with the Z-axis. What you're seeing there is with inertia active control on the Z-axis and then with the B-axis. You notice the speed difference between the two different sides there. Very simple to set up, very simple to take advantage of this technology. So what does that mean? Let's talk about a real-world application. This is a steering gear housing. This is a real application that one of our customers ran. This was running on 2 A61NX machines. It's a 500 millimeter pallet size horizontal machining center. They were doing 120,000 parts a year. They had an Op20 and Op30 that required 20 tools. So the Op20 and Op30 were on the same pallet. Because of the number of tools that were going across there, they had features on 9 different faces. So there's a lot of B-axis motion on this particular job. They put this onto the A61 and they ran it without inertia active control, so right out of the box. And then they ran the optimization for the inertia active control. And what that did for them is it took 3% out of the cycle time. Doesn't seem like much, does it? But you look at that over an annual production on just one machine. That was another 3,200 parts that they could cut, package up, ship to their customer, and get paid for just by turning on inertia active control. So another key technology that's going to help cut down on that cycle time, which is that key factor in productivity on these die-cast parts. Another one is what we call geometric intelligence milling. This gives us the ability to control the path that the spindle takes from feature to feature, okay? If you leave the machine as it comes out of the box, it will follow the path to the T, okay? If I really don't mind if it rounds a corner by a couple of tenths, it actually will speed the machine up because it doesn't have to abide by those sharp corners as it goes point to point. A couple of paths here, and you look at the dots that you see up on the screen. If I'm going to abide by the point to point, I'm constantly acceleration and decelerating as I get to each destination. Versus if I can give it a small bandwidth, and we're not talking much, we're talking tenths, allow it to flow around that path and give it some leeway on each side of the theoretical path, it will run faster. That's called geometric intelligence. And again, it's an M code or it's a toggle button on the screen. And here are two paths running, one with GI milling on and one with GI milling off. And you can see the difference, 35%. So if you've got a mill that's going around a cover face of a part, you don't care if it deviates from that program path by a thou or so. If you're going up against the shoulder and you wanted to follow that path to the T, use the M code and say you can't do that here. But if there's other areas on that part where you can allow it to flow freely through that motion, you're going to save cycle time. How about drilling? What can we do with drilling? We have a feature called GI drilling on the machines as well, where theoretically if you run a G81 can cycle, it's going to follow that red path. It's going to position to the hole, it's going to drill it, it's going to come out to the R plane, and it's going to move down to the next hole and then move in. You get a square curve as it moves through the process. But if we allow it to do what we call GI drilling, it's going to arc between the R planes, okay? You define what the R plane is, so if you've got a post or something that's in the way, it's going to abide by that R plane and it's going to jump over obstacles. But where it's out in free space, it's allowed to round those corners. And that, again, is going to save us cycle time. The red holes being run with and without GI drilling, 15%. We just picked up 15% in one case and 35% in the other just by hitting a button on the control. All right, so we've talked a little bit about reduction of inertia and what that's done for us. We've gone into the spindle design and demonstrated what that rotational inertia did. Talked a little bit about advanced motion control. All of these are going to help you make your parts faster. So here's some examples. Let's talk about real world. Bring that all together into some real world examples. Here's a gearbox. There's 3 different operations, 27 total tools, 19 total B indexes. So we make this part, there's one half that's produced, the other half is machined, they bolt them together, they machine the assembly complete. That's the 3 ops, okay? Running it on the A40, ran in 227 seconds. Running it on another horizontal, another 400 millimeter horizontal, ran at 319. And then a third one running at 337. That shows you that design for near net shape, it's going to pay off. And 29 to 33% savings on the overall cycle time. What that's going to mean is that at the right production volume, that's going to reduce the number of machines that you need to have sitting on your floor. Here's another one, steering gear housing. 2 examples, running it on an A40, 376 seconds versus running it on a traditional 4-axis horizontal, 474. So 21% improvement in cycle time. Diff case, not as big savings here, but the reason why is, number 1, there's fewer tools, and number 2, there's no B indexes at all, okay? So that was a couple of the areas where we were picking up some cycle time as having the speed of the B axis and having the acceleration, deceleration savings from the tool changes. So fewer tools, fewer B indexes, not quite as much savings, but there's still some value there. So, you know, if you come up and say, you know, how much is this part going to save me running it on a machine that's built for die cast? It's hard to say. You know, your mileage is going to vary. It depends on the content that's in that part. So that's a little bit about design for die cast components. Let's talk a little bit about some of the things that we see in the future, some of the things that are going on today. First one is new materials. There's some research going on right now. If you remember earlier, I talked about the benefit of reducing mass. There's some research going on that Makino is actually a participant in to develop some new materials. Some materials that can be used inside of machining centers beyond the traditional gray cast iron, meonite cast iron that most machine tools are made out of. And we're working with a casting company and a metal manufacturer to create a composite material that's called Athium that gives us the same basic rigidity as cast iron, but it's 60% of the weight. So think back to my earlier slides and that impact of reducing that weight. So if you were to make some of the key moving components of this machine out of a different material that gave you the strength and rigidity that you need but had a lot less mass, there's an advantage to that, okay? This is a developing technology. It's a ways out yet, but I just wanted to give you kind of a glimpse at some of the things that are in the works. This is a simulation of a machine with gray cast iron column versus one that has a Athium column. So significantly better performance. The other thing I'd like to talk about a little bit is the trends that we see going on in the industry. You remember early in the presentation I said there's 100 parts in the typical automotive, but that part number, that part count is falling. And it's falling because of stuff that you may have seen in the newspaper and some of the trade journals. Because of things like Tesla's one of them, Volvo's another one, where they're making these giga castings or these mega castings. And what they're doing is they're taking multiple parts and they're integrating them in together. And you know, there's a couple of looks at it. The one on the left there is the giga casting from Tesla. That literally goes from essentially the back seat of the car all the way to the bumper at the trunk and side to side, one piece, where that used to be numerous stampings, castings that were all assembled together. And so they're moving more to these very large, monolithic, single castings. And it's creating a big change in the industry. And right now, there's nobody out there that's really ready to address that big change. Here's the example of the Volvo, very similar. In just a massive casting. And the reason that they're doing this is if you can get rid of casting, stamping, extrusions, weldments, integrate them into a single piece, it takes assembly time out, it takes quality time out, it eliminates some of the needs for the multiple capital equipment to create those individual components. So it's extremely attractive to the OEMs to move in this direction. And we're seeing some of them being upwards of 70 parts going into one single part. It's good news for the OEMs. It's bad news for you guys if you're doing die casting because, number one, the fallout on these complex parts is really high at the moment. And then if you are getting the parts successfully off of there, the challenges of machining them are big. Because number one, the parts are much bigger and they've got features coming in from all different kinds of angles. You know, another reason why they're doing this is, big reason is the fuel economy, is it gets weight out of the vehicles, okay? And here's kind of a look at who's doing it. Who's big on it right now is Audi, Mercedes, Tesla, BMW, Volvo. They're all moving towards these really complex die-cast components that are integrating multiple pieces together. One that at the moment is kind of shying away from it is Toyota and Honda, and some of the others kind of have their feet in both camps and they're seeing which one's going to work out best for them. Okay? So with that, kind of gave you a little rundown of the ROI design, why a purpose-built machine is important and how cycle time is crucial to really maximizing your profitability on these parts, and then give you a glimpse at some of what we see as the industry trends. So, okay, thank you very much.
Hello, everybody. Thanks for joining us. Hope you enjoyed that presentation. We're really happy that we have Dave here for some questions and answers. Thanks for joining us, Dave.
Sure, glad to be here.
And so anyone out there that has a question, go into the Q&A area or the chat area, put in your question, and we're going to take those and answer those. Dave, you were talking in your presentation about the A55 back in the 90s. I know you have a wealth of experience. You've been in the industry for 30 plus years. You started out as an application engineer. You saw that machine. You put your hands on that machine. You've seen a lot of changes over the years. What are some of the things that stand out to you?
It's really interesting to be able to see the changes that have kind of rolled through the machine tool industry over the years. When I first started doing some turnkey work, we were on boxway machines, and that was the state-of-the-art technology. And the premium machines were big boxway machines, and they were very accurate, but they were very slow by today's standards. And as the changes have kind of percolated in, the first big one to really come into play was the move from the boxway design to linear guides. And linear guides dramatically sped up the performance of the machine, reduced the cycle time, and eliminated a lot of friction. So it improved the longevity and the lifespan of the machine tools. And there's been just a constant move towards faster and faster. As I pointed out about some of the newer technologies like the linear motors, going as fast as over 100 meters a minute from a positioning standpoint. But at some point in time, there's a diminishing returns on that, and it looks great on paper, it looks impressive on paper, but when you get it out there on the factory floor and try to take advantage of that, unless you've got very unique parts, you're really not going to be able to take advantage of it. So we kind of have to look at technology with a kind of you got to look at it with a very neutral perspective and see what is really going to give us. What are we trying to measure? What are we trying to accomplish? And which technology is going to deliver that for us?
And Dave, that brings us to the first question we're going to get into. And this question, it kind of reminds me, in my neighborhood, we've got new fiber optics being brought in, so much faster internet speeds, and they're advertising up to 2 gig of speeds. And they're trying to sell me on that higher, more expensive plan. But I realized that the devices that I have in my home, they can't go to that speed. I'm not going to get that benefit. And this question reminded me of that because it's talking about the faster tap speed. Why is it not an advantage potentially? You mentioned in your presentation about some of the manufacturers might advertise this very fast tap speed, but that really might make a difference for you. Can you explain a little further about what you mean by that?
Well, a tap's kind of unique in that it's got 2 characteristics to it. One is the diameter, which is going to determine, the diameter and the type of material that the tap's made out is going to tell you how fast it would like to run, and it's, how fast it's going to be happy running. But the other characteristic is the pitch, and that's how much does that tap advance in the Z direction with every revolution. And so, when you start looking at these faster sync speeds, tap synchronization speeds, that spindle truly has that capability to ramp up that fast and match the Z-axis motion with that spindle. But it's really about the part features. The part features, a typical designer will tell you that, the strength of a thread, you're going to get the maximum strength at probably about 3 to 4 times the length, 3 to 4 times the diameter is going to give you your maximum strength. And so the designers aren't going to put any more threads in than that. And because of that, as that tap starts to enter into the hole, the spindle is still accelerating by the time it reaches the bottom of the hole, and it has to anticipate that, hey, I'm at the bottom, I need to turn the opposite direction and come back out. So it'll never realize that ultra fast speed, like I said in the presentation, unless you got a really deep thread, and that doesn't exist. It's no designer's going to build that into a part.
That makes perfect sense. And we have another question here, Dave. Looking at the A40, which is one of the machines that we talked about and some of the advantages that from these design features you can gain, we have another great product, the A51NX. And this question is asking about the differences, in particular around the X, Y, and Z travel lengths. So comparing the A40 and the A51NX, what would you say about that?
They are pretty much like brothers. On the outside and on the spec sheet, they're almost going to look like twin brothers. The X, Y, and Z are relatively identical. The spindle speed's a little bit slower. Standard on the A40, it's a 12,000 RPM spindle versus the 14,000 RPM on the A51. But if you don't have a lot of very tiny features, very tiny tools that you're going to be using in your die cast part, which is fairly rare in die casting, you're really going to see a benefit from the A40. In fact, a number of the comparison slides that were in that presentation were comparing the A40 against our A51. So you might say, Makino, why are you you're cannibalizing your own product. They're both 400 millimeter machines. Why would you make two of them? Well, the one is very purpose built for die cast work. And if I had my choice, that's what I would buy if I was making die cast parts. But if I'm a job shop and I don't know what's coming through the door tomorrow, some of it may require a 1/4 inch mill cut on a 4-inch face mill. I'm not going to want to have an A40. I'm not going to ask an A40 to do that because it just doesn't have that capability. Whereas the A51 is more of a general purpose workhorse, and whatever you want to throw at it, it's going to be ready for it.
So there's some trade-offs and advantages from one platform to the other. And
absolutely.
I'll just take this opportunity also to remind everybody, if you go to the handouts up in the top right, we have the A40 brochure. You can download that. And if you have any other questions about that product, the A51NX or any others, please reach out to us and we'll have someone get back with you, get the information you need. And another question related to what you were just talking about, Dave. So the A40, we talked about die cast parts, and I loved how you said, the knuckle drag down the Home Depot. I enjoy doing that. I think a lot of us do. I'll just sometimes cruise those aisles looking at things. A lot of die cast parts on those shelves, as you said. So the A40, as you're describing, very good for those near net shape parts. But are these type of features that you talked about with the A40, are they only beneficial to machine die cast parts?
No. And that's, to say it's built for die cast is a little bit of makes it a little confusing because it goes beyond that. If you're making parts that are near net shape, so your incoming material is very close in size to the final product. These type of design characteristics in the A40 specifically are great choices. Some of the things that you might see, a lot of medical parts are coming out of investment castings. They're near net shape. Maybe it's a forging, but there's only 1 millimeter or 2 of stock on there. So even though these are challenging materials like cobalt chrome, like titanium, it's still a decent consideration for that. Metal injection molded parts, very close to the final dimensions. That'd be a great solution for that. You're seeing more and more in the news about additive. Additive's really cool technology. There's very few additive parts that don't require some degree of additional processing with a subtractive process to machine and get the tolerances that they need. But just by their nature, those additive parts, there's not much stock on there that you have to take off. So if you're trying to do a secondary operation on an additive part, it's great for that. Fine blanked parts, where it's a stamping process and you're stamping out very close to the final shape. That's a good solution if you got secondary operations for that. So it's not just die cast parts. If you look at it more as a near net shape solution, that's probably a better way to look at it.
Okay, and the next question, Dave. This question has cycle time in it. And before I get to that question, and it just reminds me to point out to everybody, we have lots of other great content for you. You can go to Makino.com, go to our resources page, go to webinars on demand. We have a series of webinars there on cycle time reduction. So look for that. A lot of other great content on our machine platforms and other things are going to help you get the most out of your machines. You also can go to our YouTube channel, Makino, and you can find a lot of those videos there as well. And if you can't find what you're looking for, again, reach out to us and we'll send it to you. We'll point you in the right direction. So Dave, this question is saying that, of course, you pointed out cycle time. It is important, right? You really hammered that point home. And this question is asking about what other things should we think about? We understand cycle time is important, but what else should we consider when we're picking out a machine, in particular for die-cast parts?
So that's a good question. I like that. And maybe I stressed the cycle time too much. We've only got so many minutes for a presentation, but there are certainly other things to consider. I guess the first one that comes to mind for me is reliability. Although I talked about the importance of cycle time and how it's the single most important factor for reducing your per piece cost, if you don't have the reliability on that machine and you lose a weight cover, as an example, it's just a simple piece of sheet metal. If that piece of sheet metal gets crumpled up and the machine is no longer protecting the critical weight structure, that machine's down. And so it takes a lot of cycle time savings to make up for downtime. So unplanned downtime is critical. I would encourage anybody looking for a machine to think very seriously about the design that goes into that machine. What is the builder doing to eliminate downtime, eliminate unplanned downtime? As an example, single piece weight covers, instead of the tented multi-piece weight covers, a single piece is going to be much more robust and give you much better reliability. You're not going to have the downtime with that kind of solution. Another thing to consider is technologies. One that I can recommend that here at Makino we offer is something called MH-Max, which is sensors that we will integrate into the machine so that it will watch the performance of the spindle, the coolant temperature, the key systems, and it will alert you if it sees a degradation over time. A lot of these machines are in for 10, 12, 15 years, and they'll start out super reliable, but over time of running 24/7 production, they get tired and they start to wear out, and systems need to be maintained and sometimes replaced. And having a system like an MH-Max system that's going to alert you ahead of time that, hey, this particular system is starting to show some fatigue, some indications that it's about to fail. And if you can, shut that machine down on a convenient time and on a planned time to do that preventative maintenance, that's going to help you eliminate, production surprises of that unplanned downtime.
And to add on to that, that discussion about unplanned downtime, as you were just pointing out, we've got a lot of great product features, the reliability of our machines, but Makino has also invested a lot in the infrastructure to support these machines. So that you have the spare parts you need, you have the trained field service engineers you need close to you. If you look at the training that Makino does, it is top notch. You look at the documentation that's provided. If you do a turnkey with Makino, all the documentation is provided, everything to help you make sure that you're able to keep that machine up and running, avoid unplanned downtime. Bringing all that together really makes a difference.
Yeah.
Dave, I want to thank you. I want to thank the audience for joining us. Appreciate all the questions, and I want you all to have a great day. Thank you.
Thanks, folks.